Welcome to today's Masterclass Explainer. Have you ever watched a heavy insect just casually stroll across a pond? Or maybe you've wondered how massive trees manage to pull water hundreds of feet up into the air? Well, you're already observing some of the most fascinating, unseen physical forces in our everyday world. Today, we're diving deep to unlock the mechanics behind fluid behavior. We'll be your guide through the invisible architecture of water.
Here's our roadmap for today's session. We're going to start with the floating paperclip phenomenon, dive into the molecular physics behind it, break down the pressure formulas, explore contact angles, explain capillary action, and finally, look at some crucial engineering applications.
All right, let's jump straight into part one, the floating paperclip. So, imagine gently placing a metal paperclip perfectly flat onto the surface of a bowl of water. It floats. But wait a second, metal is significantly denser than water. According to Archimedes' principle, any object denser than the fluid it displaces should sink like a stone immediately. Yet, there it sits, perfectly suspended. So how on earth is this possible? The secret here is surface tension. We denote this with the Greek letter sigma. You can think of the interface between two fluids, like water and air, as being in this constant state of tension. It behaves exactly as if it were a stretched, elastic rubber membrane that is constantly trying to contract. This microscopic skin is remarkably strong. It's completely capable of supporting small weights, like our metal paperclip. Moving on to part two, molecular physics. Let's zoom way in and look at a tale of two molecules to see why this happens. Molecule A is sitting perfectly happy deep inside the bulk of the liquid. It's completely surrounded by other water molecules on all sides, meaning it's pulled equally in absolutely every direction. The net force? Zero. But now look at molecule B, perched right at the water-air interface. It's being pulled by water molecules from below and from the sides, but it's only very weakly attracted by the air molecules above it. This creates a net downward-inward force. The surface molecules are continuously being pulled inside, minimizing the surface area, and creating that tight, membrane-like tension. In physics and engineering, we need to define surface tension mathematically. The SI unit is newtons per meter. That represents the force acting along a unit length of the interface. But remember, because energy equals force times distance, newtons per meter is mathematically identical to joules per square meter. That is a really beautiful scientific truth. Surface tension is precisely the amount of energy required to create a unit area of new surface. Part 3. Pressure and formulas. Because of this inward contracting force we just talked about, the pressure inside a fluid droplet is actually higher than the pressure outside of it. If we look at a spherical droplet, we can calculate this excess pressure, which we represent as delta P. Delta P equals the internal pressure, Pi, minus the outside pressure, P0. By balancing the surface tension pulling the drop together against the internal pressure pushing it apart, we get our formula. Delta P equals 4 times sigma, divided by the droplet's diameter, d. Or, if you want to keep it even simpler, 2 times sigma divided by the radius, r. But what happens if we swap out that water droplet for a soap bubble? Well, a bubble is hollow, right? It has air on the inside and air on the outside, separated by a super thin film of liquid. This means a bubble actually has two interfaces, an inner one and an outer one. Because the surface tension force is acting along two circumferences, the excess pressure inside a bubble is exactly double that of a solid droplet. So for a bubble, delta P equals 8 times sigma divided by the diameter. All right, let's look at part 4, contact angles. Up until now, our droplets and bubbles have just involved two phases, liquid and gas. But what happens when we introduce a third phase, like a solid surface? When a drop of water rests on a solid surface, it forms a very specific angle, known as the contact angle, or theta. If theta is less than 90 degrees, the surface is hydrophilic, or water-loving. The liquid just spreads out, like you'd see on a piece of glass or some cotton. But if theta is greater than 90 degrees, the surface is hydrophobic, water-fearing. Think of polymers or rubber. A brilliant natural example of this is the lotus leaf. It has these incredible microscopic patterns that make it super hydrophobic, giving it a contact angle of over 150 degrees. Water forms perfect spheres and just rolls right off, completely clearing away dirt as it goes. Which brings us perfectly to part 5, capillary action. Understanding those contact angles is the key to unlocking capillarity. Capillarity is the rise or fall of a liquid inside a very narrow tube, which looks like it's completely defying gravity. This happens because of surface tension along that exact three-phase contact line we just mentioned, where the solid tube, the liquid, and the air all meet. To figure out exactly how high that water will climb, we use the capillary rise formula. The height, h, equals 2 times the surface tension, sigma, multiplied by the cosine of the contact angle, theta. We then divide all of that by the density of the liquid, rho, times gravity, g, times the radius of the tube, r. Essentially, the surface tension is pulling the liquid up the walls of the tube, while the physical weight of the water column pulls it back down. When those two forces finally equalize, the rise stops. Now, the math here reveals a totally fascinating exception. What if the surface is highly hydrophobic and our contact angle theta is greater than 90 degrees? Well, the cosine of any angle between 90 and 180 degrees is a negative number. This means our height, h, actually becomes negative. The liquid isn't pulled up at all, it's pushed down. If you were to dip a glass capillary tube into liquid mercury, the level inside the tube actually falls below the free surface outside of it. It's pretty wild to see in person.
Let's bring this into the real world with Part 6 engineering applications.
In civil engineering, mastering these exact equations is absolutely non-negotiable. Think about soil mechanics. In fine-grained soils, like clay, the tiny pores between dirt particles act exactly like microscopic capillary tubes. Capillary rise in these soils can actually reach several meters vertically. This dramatically affects soil moisture, strength, and overall foundation stability. It also dictates how concrete and bricks absorb water, which directly impacts a building's durability over time. Engineers are constantly designing damp-proof courses and capillary breaks to stop this upward creep of moisture from completely rotting out structural foundations. And it's amazing to think that these massive engineering concepts are driven by the exact same principles powering our everyday world. Surface tension is what supports that water-walking insect we talked about, and it's what forces water into perfect spheres on lotus leaves. Meanwhile, capillary action is the exact mechanism that lets a cotton towel wick moisture right off your hands, and it's exactly how the roots of plants manage to draw groundwater deep up into their stems against the relentless pull of gravity. It's also incredibly vital to remember that these properties vary wildly depending on the material and the environmental conditions. At room temperature, water's surface tension sits at about 0.072 newtons per meter. Mercury, on the other hand, is incredibly tight. It sits way up at 0.485 newtons per meter. Temperature plays a massive role here too. Heating water increases its molecular activity, which weakens the attractive forces between the molecules. This actively lowers the surface tension, which, by the way, is exactly why hot water is so much better at penetrating fabrics and getting your clothes clean. All right, before we wrap up, I have a little observation homework for you to take this masterclass out into the real world. First, try putting a drop of water on a clean glass plate, and then another on a wax surface, and compare the contact angles for yourself. Second, next time you're near a garden after it rains, spot how surface tension forces those water droplets into tight spheres on the plant leaves to minimize their surface area. And finally, put a very thin drinking straw into a glass of water and watch how the liquid level inside the straw rises just slightly higher than the liquid in the rest of the glass. We've seen today how a seemingly microscopic imbalance of forces creates an elastic skin powerful enough to float heavy metal, perfectly shaped bubbles, and draw groundwater upward against gravity itself. But I want to leave you with this final provocative thought. If capillary action is constantly lifting water meters high through the soil beneath our feet, what exactly happens to the stability of a massive skyscraper's foundation when seasonal changes cause those billions of microscopic structural water skins to suddenly dry up, or worse, freeze? Keep observing the world around you, keep questioning how it works, and I will see you in the next explainer.